everyone, thank you for joining my talk today on coupling of evacuation and fire modeling through Soot level analysis. My name is Cheong, and this desktop study has been carried out with Kelvin Low, Dr. Arnab Majumdar, and Professor Washington Yoto Ocheng, and we are all from Imperial College London. Today, I will cover why such a coupling using Soot level analysis is important, and what has been done in the past, and what we propose as an additional methodology when compared between standard visibility assessment and proposed, and discuss the results and end there. When we look at the well-known ASET and RSET relationship, particularly the movement time can vary depending on the tenability condition and that the evacuees are faced with. The typical quantified tenability conditions when referring to NFPA 130 are visibility, fractional effective doses, and temperature. On your right, you see 4 sets of RSET, ASET representation from a confidential tunnel project I have worked on in the past. On the x-axis, you have the chainage along the tunnel, and on the y-axis, the time passed from fire initiation. The worst-case fire location for this particular scenario was considered to be a chainage of 650 meters. The egress path from the fire location is along the black line based on the assumption of walking speed of 1 meters per second. Our analysis showed that along the egress path from the fire, the untenable condition at head height is predicted to be reached by visibility factor the most. Based on this, the preliminary conclusion was that visibility is a crucial tenability criteria. Of course, we are not the first one to attempt the coupling. There are many presenters and attendees at this very conference who have carried them out in the past or are carrying them out today. A lot of coupling uses FDS for the fire model, and for evacuation modeling, Pathfinder, STEPS, and FDS plus evac have been popular. University of Greenwich use their own building exodus and SmartFire for their coupling. These couplings, to our knowledge, use local visibility values for evacuation analysis. In terms of evacuation modeling, we use MassMotion from Oasys and its software development kit so that we can influence the agent's decision-making process and walking speed in a systemic way. In our case, we have used the programming language of Python. So the current practice in the industry is to consider the local visibility values at head height, which according to NFPA 502 is considered to be 2.5 meters to account for modeling errors. However, when only the local visibility values are considered, the agent's exit selection can seem somewhat unintuitive, as this means the agent would power through dense smoke without changing routes. So our assumption is that if evacuees see a cloud of smoke, when they look in the direction of the exit, they may choose a different path to evacuate to avoid the smoke. This would then have a different evacuation dynamic, and modeling this is exactly our aim. It wouldn't be a visibility research without considering Jin's experiment in the 70s, where people's walking speed has been measured against visibility impacted by smoke from a real fire. Here you see that the analysis shows only up to a low extinction coefficient. Extinction coefficient is ultimately the inverse of visibility. The experiment showed that with lower visibility, or higher extinction coefficient, the walking speed would decrease. An update or an alternative relationship study based on experiments have been carried out by Francis and Nielsen in 2003, where they have considered extinction coefficient of higher than 1.2 per meter. In other words, for much lower visibility conditions. These data sets have been converted into a formula by Friedolf and others. The relationship calculates the resulting walking speed through the smoke as the minimum of unimpeded walking speed and the walking speed impacted by the smoke. Also, the study stated that at a certain visibility, the physical ability of oneself has a negligible impact on the resulting walking speed. To consider non-local visibility values, Kang in 2005 considered a ray tracing method of having a camera set up for every agent and casting multiple rays, calculating the dimming of the pixels. This, however, not only assumes a homogeneous smoke layer, but also the computational resource cost grows exponentially once the number of agents is greater than 1. Considering research outside of the evacuation field, Labelle studies the physiology of human vision and shows that the preferred vision area is actually quite narrow, and non-visually impaired people fixate on a point over a distance, which helped us formulate a single ray method. Shooting a single ray has been considered before, particularly by He. He calculates the average extinction coefficient along the line of sight to measure the tenability. However, we believe averaging the extinction coefficient can lower the resulting evaluated extinction coefficient compared to when using the local value. Using the studies found, our methodology was a one-way coupling where we share the same geometry inputs for our fire model and our evacuation model. From the fire model, we take the outputs of visibility and Soot level at different time steps and put it into our visibility Soot methods to recalculate the walking speed and exit selection and therefore the direction of the agent. The visibility Soot algorithm essentially consists of 2 steps. The walking speed is impacted by the local visibility as per literature, particularly the relationship formed by Friedhoff et al. This, however, does not impact the direction of the agent movement. The second step is considering the Soot levels along the line of sight. A single ray is casted onto all the exits from the agent's location at head height. Then the maximum Soot yield is recorded and compared to a threshold to select the exit. The important aspect to consider in this case is the threshold. The threshold has been chosen based on the work carried out by Berginski and Vigne, who studied the influence of Soot yield on the visibility. One of their conclusions was that Soot yield below 0.1 grams per grams requires extreme caution when applied to ASET RSET analysis. So for our desktop study, the value of 0.1 has been chosen. One of the future aspects to consider for the study is verifying and varying this threshold. So let's get into the work we have carried out. The geometry we consider is a 50 meter by 50 meter, similar to what Fang et al. Have used for their coupling work. Although the purpose of their work was to apply multi-grid method to FDS plus evac and not alter how visibility is used in the evacuation process. In our geometry, 2 exits and a smoke extraction system have been implemented as per the UK building regulations, and a fire source representing a sofa with materials such as polyurethane was implemented in the center of the room. On the evacuation modeling side, 30 homogeneous agents are implemented with a lower standard variation within a Gaussian distribution for the pre-evacuation time and unimpeded agent speed. The agents are introduced in various locations of the room prior to the model start and circulated to warm up the simulation and have a spatially balanced distribution of agents over the room floor. Other than the pre-evacuation time, to sync the fire initiation and evacuation modeling, a detection time and alarm time of 1 minute have been assumed. So what do the results look like? The simulation was run 3 different ways, using the same random seed. The first method presents the evacuation model only without the consideration of fire, so this is our baseline. The second method applies only the impact of visibility on the walking speed, as you applied by many others. The third method is our proposed method of using visibility to impact the walking speed and Soot levels along the line of sight to impact the exit selection. The top image is of smoke view from the moment the average evacuation movement starts. As you can see by the graphics, the evacuation time varies, and consideration of Soot levels actually decreases the evacuation time in this case. When observing the paths that the agents have taken, obviously the first two methods would provide the same paths, as in the second simulation the visibility factor only changes the walking speed. As for the results for our method, you see that the agents have generally avoided the center of the room where the fire is, and agents have turned around to not go through the area with high Soot yield. When evaluating the densities across the room, the maximum Freund level of service categories don't change amongst the three methods, but the areas of the higher densities vary. Whereas an uncoupled evacuation model shows high density value along the paths, the coupled methods show high densities around the exit, which we observe in real evacuation scenarios. To put some numbers to the comparisons, as one of the disadvantages of the Kant's ray casting method is the computational cost. So we showed that using a single ray method does not significantly increase the computational power requirement compared to the method where only visibility is considered. Secondly, the total movement time varied, but most importantly, the exit selections varied as well when considering the Soot level along the line of sight of each evacuee. So to quickly discuss the results, incorporating the Soot level analysis has shown different evacuation dynamic at a very small increase of simulation time. Further aspects to consider for this study are verification and validation, evaluation of the Soot yield thresholds, different geometries with physical obstacles blocking the way to an exit or an exit sign. So to summarize, Soot level analysis was incorporated for evacuation modeling in our desktop study, particularly for exit selection through a one-way fire and evacuation modeling coupling. Results show different evacuation dynamic, and in the future, particularly the Soot level thresholds need to be further investigated. We would like to thank Lloyd's Register Foundation and UKRI for funding this project, and Oasys for providing us the commercial software of MassMotion, and Dr. Mohammed Tabara and Amir Pornasser for the advice they have given us from Arup, and Robert, Camille, and Alex from our PhD cohort for the detailed initial discussion. Thank you for your time, and thank you for listening to my talk today.
Okay, so we're live now, so we'll just wait for people to make their way over from the stage, and we'll start our Q&A. And let's see, make sure I'm in the right chat. There we go, now I can see. Okay, so we're starting to see the numbers climb up as people make their way over. You're welcome to ask questions. Oh, here we go. All right, so first question is the choice of exit in singular event or occupant would reevaluate the choice if suddenly the soot appears in front of them? This can happen rather easily in complex multi-floor compartments like lobbies and malls. So how do they make the choice periodically, or is it just like a one kind of a
They
single
make
event?
the choice at every time step. So
Okay.
the time step is currently at 1 second.
Okay, so every second they have the option to make it reselect a choice. Great.
Yes.
And then have you thought about how to consider the impact of ambient lighting or light emitting objects on visibility?
We haven't. So we use the standard, I think we use the C value of 3 for the FDS model. So we would need to change within FDS. Yeah.
Okay, great. So you were using the visibility data output from FDS, the Soot visibility value to make the choices. Yep.
Yeah, so it was Soot mass fraction. So the idea came from reading from Woods in 1972, where he did an experiment where he had smoke in a building, and then he saw that people would change their direction depending on the smoke levels.
Mm-hmm.
So it is explained a bit more detailed in the paper.
Yeah, and that's a good reminder that there is a paper for all of these talks that will be available in the archive pages after the fact, so you'll be able to get more information on that. What's the basis for soot yield of 0.1 kilogram per kilogram for the ASET RSET exercise, and how significantly would the visibility change if we're to use a soot yield of, let's say, 0.05 kilograms per kilogram mass fraction?
That's a good question. Actually, my information was taken from Vekjinsky's paper, who is the next speaker, I think. So I do reference the paper in the PDF of the paper that I wrote. So it's detailed more there. We haven't quite considered it.
Okay, great. And then another question here. Have you considered, I think it's cellular automata model or social force model, or just applied the algorithm with the ray comparison?
So for this study, we only did the algorithm with the ray comparison. This study actually is part of a bigger project where we do look at social force models, and where we also look at decision-making models and so on. But this particular part was only looking at visibility and soot levels.
Great. Okay. And let's see if there's any other questions. We'll just give it a minute. Yep. So I don't see anything coming up right away. If you see any more come into the session chat, you're welcome to answer with text there and address those. Just to give everybody a little heads up, this morning we enabled a feature that allows you to look people up who are attending and have one-on-one conversations and even video chats. So you can text or you can start a one-on-one conversation with video. You'll need to refresh your browser, and where you see chat and polls, you'll also now see a people tab. And so you can kind of maybe see that in the stage preview. You'll see chat polls and people above the event and session toggle. So you'll get that if you refresh your browser. You'll be able to go in there, search by name, find people, start a chat, and go on from there. So it hopefully will be a useful feature for everybody and allow you to reconnect with those you've already maybe chatted with in networking that you'd like to follow up with. So other than that, thank you so much, Haein, for this Q&A, for your presentation. It was really, really interesting. And hope to see you around in the conference. Thank you.
Yes. Thank you. Bye.
Bye-bye.